Hello, everybody, and welcome back. We are going to go through Chapter 6, Section 6.4 and 6.5 on the real numbers with irrational numbers, decimals, and percents. Hopefully, you've had an opportunity to read those chapter sections. These will not be covered on Test 1, but rather are going to be covered on Test 2. In section 6.4, we're talking about irrational numbers, and we talked a little bit about these last time. The definition of an irrational number is here, decimals that neither terminate nor repeat. And in set notation formula, they are written as irrational. The set of irrational numbers are those numbers x, where x is a number represented by a non-repeating, non-terminating decimal. And they also cannot be represented by a quotient of integers. Some of the numbers that we had talked about previously that were irrational numbers, you can see on page 255, the square root of 2, and pi, the ratio of the circumference of a circle to its diameter. There are infinitely many irrational numbers. As we talk about other factors concerning real numbers, there are the square roots. And as we talked about last time, the square root is a number that, when multiplied by itself, gives you the number that's underneath the square root symbol. So if n is a positive integer that's not the square of an integer, then the square root of n is an irrational number. So for instance, if n is 9, the square root of 9 is 3. Though n is a positive integer, but it is a square of an integer, which is 3. But if you look at the square root of 3, and that not being a square of an integer, the square root of 3 would be an irrational number. For non-negative real numbers a and b, the square root of a times the square root of b equals the square root of a times b. Now turn in your book to page 261, and you can see some examples about this. So, page 261, let's look at number 25. The number 25 is written as the square root of 50. And what the square root of 50 is, if you think about what 50 is, we have the square root of 5 times the square root of 5 times the square root of 2. The 5 times 2 is 10, and 10 times 5 is 50. However, the square root of 5 times the square root of 5 is the square root of 25 times the square root of 2. And this is just, since 25 is a square of integers, 5, the square root of 25 is 5. The answer for this, or the simplification of this, is 5 times the square root of 2. This is what we call simplifying the expression. Now, if we were to take this and plug these numbers into a calculator, we would take the square root of 2, square root of that, times 5, and we would get about 7.071. Since the square root of 2 is irrational, that expression would continue on for a large number of digits. Another example would be number 26 on that same page, the square root of 32. 32 is the product of 16 times 2. So the square root of 16 times the square root of 2. 16 is a square of integers. So this gives us 4 times the square root of 2 is the simplified version. And we take the square root of 2 and we find the square root of 2 using a calculator and multiply that by 4. And we get about 5.6568. Another example here is number 27, the square root of 75. 75 is just 25 times 3, so the square root of 75 is the square root of 25 times the square root of 3. We saw from up here that the square root of 25 is 5. It's a square of integers times the square root of 3. So 5 times the square root of 3 is the simplification of the square root of 75. Again, you take the square root of 3 and multiply it by 5, and you get a number something like 8.66. And lastly, number 28 is a little bit larger number, square root of 150. We can break this down again into square root of 25 times the square root of 6. Square root of 25 again is 5. Square root of 6 is square root of 6. We plug that number into a calculator and find out the square root. Since it's not the square of integers, it is an irrational number. And we get a number like 12.247. So those are examples of if you have non-negative real numbers a and b, and you have two square roots together, it's the same as the square root of the product itself. We also can simplify square roots. We simplify square roots by taking the factor apart. So as indicated before, the square root symbol is there, but the symbol itself is called a radical. So sometimes you may hear me refer to this term as a radical. It's used to identify the square root. The number under the radical is called a radicand and has no factor except one that's a perfect square. There are no fractions allowed in the radicand, and no denominator can contain a radical. This is just a rule of radicals. No denominator can be in a fraction that's under the radical symbol. So let's look at an example here. If you turn to page 257, you'll see that a problem is given you to simplify the square root of 27. And we know from our previous exercises that this is the same as the square root of 9 times the square root of 3. 9 times 3 is 27. And the rule that we had indicated earlier is the same. So the square root of 9 is 3 times the square root of 3. So that example is really the same as what we looked at before. So going back to our slides, there is a rule for square roots. This rule is that if you have a fraction that contains radicals, a radical A over radical B, that's the same as the radical of the fraction itself. As long as your real numbers A and B are non-negative for A and positive for B. There are some examples on page 257 below this this other example here. And I'll let you take a look at those on your own. Example 2, page 257. But let's also look at number 33. Number 33 gives us a fraction, square root of 7 over 4. Remember, this is the same thing as saying square root of 7 over the square root of 4. And we have in the denominator, that is the number below the quotient symbol here, the dividing line, a perfect square. So square root of 7 divided by 2. And since 7 is an irrational number, if you took that number and plugged it into a calculator, divided it by 2, you'd wind up getting a number close to 1.3228. In number 34, this one's a little trickier because we are looking at the fact that a denominator cannot contain a radical. So what we have here is the square root of 8 divided by the square root of 9. The square root of 8 is not in itself a product of squares, of integers, but it can be broken down further. So the square root of 8 is the same as the square root of 4 times the square root of 2. The square root of 9 is 3. Square root of 4 is 2. So what we're left with here, simplified, is 2 times the square root of 2 divided by 3. And again, we plug that into a calculator, and we get a number close to 0.9428. Now look at number 35. 35 is a little bit different. Now let's clear this. 35 is a little bit different because what we want to do here is we want to say, okay, it's square root of 7 over 3. Now remember the rule that you cannot have a radical in the denominator. So what we have here is square root of 7 divided by the square root of 3. Well, we can't have that because there is a radical in the denominator. So what do we do to get rid of that? Well, remember that any number divided by itself is 1. So we are going to multiply the whole thing times 1. We're allowed to do that. Multiplying any number by 1 is just that same number. It might be in a different form. So what we have here is square root of 7 times square root of 3 is the square root of 21 in the numerator, divided by the square root of 3 times the square root of 3, which is 3. Now we plug in the square root of 21 into a calculator, divide it by 3, we get a number something like 1.527. Okay, the key here is that these, it's okay to multiply a number by 1, which can be in any form. A number divided by itself is always going to be 1. The only number that doesn't work in this way is 0. Look at number 36. 36 is similar. 36 has a square root of 14 over 5. This is the same as the square root of 14 divided by the square root of 5. Again, we multiply any number divided by itself to get rid of the radical in the denominator. Square root of 14 times the square root of 5 is the square root of 70 divided by the square root of 5 times the square root of 5, which is 5. So this is the simplified fraction format of that, and if you plug that into a calculator to get the real number, divide that by 5, you get a number close to 1.6733. So those are illustrations of the quotient rule for square roots. Now, there is a function called adding and subtracting square root radicals. We can add or subtract them if they're similar, as long as the radicals are the same. We call these like radicals. This would be using the distributive property. The example for this is example number 3 on page 258, and I'll leave you to that to take a look at. But what we're going to do is look at these other problems from the exercises in section 6.4. So if you turn to those on page 262, we'll go back to the whiteboard here. If you look at number 37, this is fairly straightforward. As long as the radicals, if you're adding radicals, you have the square root of 17 plus 2 times the square root of 17. As long as the radicals are the same, you can add them together. So how many square roots of 17 are here? There's one implied that there's only one of these. Okay, there are 2 of these. So 1 square roots of 17 plus 2 square roots of 17 equals 3 square roots of 17. And we're since 17 is not a product of integers, this is an irrational number. So as long as the radicals are the same, you can add them. Add and subtract. So similarly, if we look at number 39, our problem says 5 times the square root of 7 minus the square root of 7. There are 5 square roots of 7 here, and there's only 1 square root of 7 here. So 5 square root of 7 minus 1 square roots of 7 is 4 square roots of 7. Okay, so adding and subtracting you can do with radicals as long as the radicals are the same. Now what happens if you have radicals that are not the same? Like in number 43, you have negative square root of 12 plus the square root of 75. Negative square root of 12 plus the square root of 75. Well, let's think about this for a minute. These are not obviously the same radicals. So let's break this down a little bit. Negative square root of 12 is the same as saying negative square root of 4 times 3 plus the square root of 25 times 3. Which is the same thing as saying negative square root of 4 times the square root of 3 plus the square root of 25, times the square root of 3. Well, we have two squares here that are squares of integers. So this gives us negative 2, because the square root of 4 is 2, times the square root of 3, plus 5, the square root of 25 is 5, times the square root of 3. Now we have like radicals, and we can add these together. Negative 2 square roots of 3 plus 5 square roots of 3 gives us 3 square roots of 3. So the solution to this problem is 3 times the square root of 3. The last example, or the last problem I want to review here, is number 44, 2 times the square root of 27 minus the square root of 300. Well, tell you what, let's clear this and we can start at the top with it. 2 times the square root of 27 minus the square root of 300. This is the same as saying 2 times the square root of 9 times 3. 9 times 3 is 27. Minus the square root of 100 times 3. You see where this is going? 2 times the square root of 9 times the square root of 3 minus the square root of 100 times the square root of 3. 2 times the square root of 9, square root of 9 is 3. So that would be 2 times 3 times the square root of 3 minus the square root of 100, which is 10 times the square root of 3. 2 times 3 is 6 times the square root of 3 minus 10 times the square root of 3. 6 square roots of 3 minus 10 square roots of 3 gives us negative 4 square roots of 3. So if you treat the radical, as long as you can get to the point where your radical is the same for both of them, you can add and subtract radicals quite readily. Now, getting back to irrational numbers, we had mentioned last time that the ratio of the circumference of a circle to its diameter is given by this formula, C equals pi times D. Pi is one of the classic irrational numbers. And once again, if you look at the biblical reference, 1 Kings chapter 7, verse 23 in the Old Testament, and I'm paraphrasing here, and he made the molten sea. It was round, 10 cubits from brim to brim and 5 cubits high, and a line of 30 cubits measured its circumference. So in this case, C is 30, that is, the circumference is 30, and the diameter is 10. So 30 divided by 10 is the pi, which is 3. Now, rounded to the nearest whole number, pi is 3, but we know a little bit more now than they did back in biblical times. But to the nearest whole number, it is 3. Now, there's another symbol, or another Greek letter called phi. Phi is also known as the golden ratio. Now, this is also covered in section 5.5, but this is considered the ratio of the length of a rectangle to its width being equal to the length of the ratio of the sum of the length and width to its length. Now, if you'd like to learn a little bit more about this, check out section 5.5. 5.5 in the text. Additionally, there is another irrational number called e, which is the base of the natural exponential and natural logarithm. Again, if you'd like to find out more about that, see section 8.6. Now, to illustrate the golden ratio, which is indicated here as an irrational number, there is a fun little cartoon that is on the internet that I'm going to attempt to tie in here. So please bear with me as we start, as we do that. So we'll see how that works. Mathmagic Land. It's the land of great adventure. That video can be seen on the internet if you want to see it in its entirety, or if it didn't record properly here. Do a Google search for Donald in Mathmagic Land, Mathmagic. It's a fun little video. It's less than 30 minutes long, and we didn't show the whole thing here, but that section on the golden ratio I thought was particularly interesting and fun and appropriate to illustrate the golden ratio. That's one of the key irrational numbers listed in the text. Now, in section 6.5, we talk about applications and of decimals and percents. The key here is use the technology, folks. A calculator is they're cheap nowadays, and they're very easy to use. Many people have had experiences using them, and they're almost second nature. A lot of cell phones have them as well. But if you don't have one handy, there are some ways you can add, subtract, multiply, and divide decimals. Examples are listed in the chapter, section 6.5. Looking at example 1, for addition and subtraction, and example 2 for division, gives you some illustrations on how to do those. If you look at page 272, we'll look at a couple of the exercises there. So if we look at number 11. Number 11 is 8.53 plus 2.785. Now, the way you add a decimal here is you would see that this terminates here, 8.53. We assume that anything past that would be 0, so 0 plus 5 is 5. 3 plus 8 is 11. We put the 1 from the ones column here and the 1 from the tens column here. So there's 1 10 and 1 1 and 11. And we add these together. 5 plus 1 is 6. Plus 7 is 13. So the 3 goes here, and the 1 from the 13 goes there. The decimal is brought down. The decimals are here. And then we just add these together, 8, 9, 10, 11. So the sum of these decimals is 11.315. So similarly, if you're doing subtraction, look at number 13, 8.74 minus 12.955. That's a 0. And one of the things that we can do when we are subtracting a larger number from a smaller number is realizing that the number is going to be negative. We can take the absolute value of this number, which we talked about absolute value before, 12.955, minus the absolute value of the other number, 8.740, subtract them, 5 minus 0, and we start at the right, at the farthest right numbers. 5 minus 0 is 5. 5 minus 4 is 1. 9 minus 7 is 2. Bring the decimal down. You must line the decimals up when you do this kind of calculation by hand. And 12 minus 8 is 4. Now, since we are subtracting a larger number from a smaller number, our result is going to be negative. So the solution here is negative 4.215. Same thing in number 14. We want to look at the absolute value of the negative number, since the negative number is the larger number. 3.997 minus 2.41, and that is really 2.410. The 0 is understood to be there when the number ends. So 7 minus 0 is 7. 9 minus 1 is 8. 9 minus 4 is 5. 3 minus 2 is 1. But since the original problem had a larger number being subtracted from a smaller number, the solution is negative. So this is the solution then to number 14. Now, if we're looking at multiplication, if you look at number 16, for instance, 45.1 times 8.344. If you don't have a calculator to do this, doing multiples by long multiplication is a little bit more interesting. The way it works is you start with the digit all the way in the right of the number here, the bottom number, and you say, okay, 4 times 1 is 4. 4 times 5 is 20. So you put the 0 from the 20 here, and you put the 2 up here. 4 times 4 is 16, and then you add these two. So 16 plus 2 is 8. Do the same thing with the next number from the right, so 4 times 1. But now, instead of putting the number underneath this side, you move them over by a decimal, since you're now at the next decimal here. So 4 times 1 is 4. 4 times 5 is 20. So it's the same as the other number. 4 times 4 is 16, 17, 18. Then the 3. 3 times 1 is 3. And again, we move over. 3 times 5 is 15. Now this 2 isn't there anymore. It becomes a 1. So 3 times 4 is 12, plus the 1 is 13. Then we do the lastly with the 8. 8 times 1 is 8. 8 times 5 is 40. You put the 0 from the 40 here and the 4 here. 8 times 4 is 32, plus 4 is 36. Now you see, as we did this, we moved everything over by a decimal place, and now we add these up. 4, 0 plus 4 is 4. 8 plus 3 is 11. 1 there, carry the 1. 1 plus 1 is 2, plus 8 is 10, plus 5 is 15, plus 8 is 23. So you put the 3 here and the 2 from the 23 here. Add these numbers now. 2 plus 1 is 3, plus 3 is 6. 1 plus 6 is 7, and then 3. But now you're saying, well, gosh, how many decimals are there? And the number of decimals is going to be determined by the number of spaces to the right of the decimal point that we had before. So there are 1, 2, 3, 4 total decimal places to the right. So now we look at our solution here and we count from the end. 1, 2, 3, 4. So the solution to this multiplication problem is 376.5 3144. And obviously, if you have a calculator and you key in the numbers correctly, the answer will come out a lot faster than if you do it longhand like this. But if you don't have a way to do it, this is how you do it. So I skipped ahead, or I moved ahead a little bit on the multiplication of decimals. You multiply as you would an integer, and then put the decimal place in the product, n places from the right of your answer, where n is the sum of the decimal places in the original number. That's what we just did in this last problem. In dividing in a decimal, you divide it as you would if it were an integer, but you must move the decimal point so that the divisor is a whole number. Again, there are examples on page 265 on how to do this. But let's say, for instance, that you have 0.7, and you want to see how many times 0.7 goes into 21. Now, in order to do this, what you have to do is you have to say, okay, this is the divisor, that is the number that you're dividing into. So, or you're dividing by. So how many times does the 0.7 go into 21? We must move this decimal one place over to the right. And by so doing, and the 21 is understood to have a decimal, we move a decimal over here one place. It's not a smiley face. So really what we are getting then is 7 divided into 210. So if you treat both the number outside the radical and the number inside the radical the same way, you haven't fundamentally changed the problem. So then what we do is, since this number is now a whole number, we can divide this into 210. Well, 7 does not go into 2. So we take the next 2 digits and we say, oh, 7 does go into 21, it goes in there 3 times. 7 times 21 is 3. So 7 times 21 is 3. We subtract these two, and we get from this decimal, or from this location over, we subtract. And we bring down the other number here. 7 goes into 0 times. Now the decimal had been moved here, as you recall from up here. So directly above that is where the decimal appears. So 7 into 210 is 30. Now, when we talk about rounding decimals, what we do is we take a number, and if we want to round a number up or round a number down, we locate the place which the number is being rounded to. So, for instance, if you're rounding it to the nearest tens, you look at the next digit to the right of the tens column, and if that digit's less than 5, you drop all the digits to the right of the place in step 1, and then if it's 5 or greater, you drop all the digits to the right to which the number is being rounded and add 1 to the digit in the place to which the number is being rounded. So let's look at an example here. So example 4 illustrates we have 14.39656. And we are being asked to round that to the nearest thousandth. Now, if we look at this number, we can see here are the tens, here are the ones. To the right of the decimal point are tenths. It's a T, tenths. This number is hundredths. This number is thousandths. And this number is 10,000ths. And this number is 100,000ths. 100,000ths. Now we're being asked to round it to the nearest thousandth, so that would be to here. Now if we look at our rules, we locate the place to which the number is being rounded. So we're rounding it to the nearest thousandth. The number in that digit, the digit in that place, that is a 6. We look at the next digit to the right of the place to which the number is being rounded, which is a 5. And if that digit is less than 5, we drop it. But the digit is greater than 5. So the rule is to drop all the digits to the right of the place to which the number was being rounded and add 1 to the digit in the place to which the number is being rounded. So rounding this to the nearest thousandth would be 14.397. So this is the rounded value. Okay, so that's an illustration of rounding. Also, with regard to real numbers, most people are familiar with money, especially in this country. You have 100 cents in a dollar. So the word per cent means per hundred, and the symbol is a percent symbol, which looks like this. 1% is 1 over 100, or 0.01. If we want to convert a percent to a decimal, we move the decimal point 2 places to the left and drop the percent symbol. If we want to convert it to a percent, we move it 2 places to the right, inserting zeros as placeholders if necessary, and we add a percent symbol. So for instance, if we want to let's say that we want to have percent, let's say we have a value 98%. If we want to convert this to a decimal, we move the decimal, which would be understood to be here, 98%. We move it 2 places to the left, and we get 0.98. Conversely, if you wanted to convert a decimal to a percent, we move the decimal 2 places to the right, and we're back at 98%. There are some examples in the book on page 267 about converting fractions to percents as well. When you convert a fraction to a percent, you divide it, convert the fraction to a decimal, and then you convert the decimal to the percent, the same way that we just illustrated. So take a look at the examples on page 267 on how to do that. Now, this is the last slide of this this section, but it's probably one of the most important ones, because one of the things that you're often asked to find out, figuring out the percent of a number, the percent one number is of another, finding a number of which a given number is a given percent, and how much is increased or decreased. This comes in very handy for a couple of things. In real life, if you are asked to buy your friend lunch, or you offer to buy your friend lunch, and the bill comes and you want to calculate the tip, and you decide, well, you know what, they had especially good service today, so we want to provide them with a tip of 20%. How do you know what percent to add to your payment so that your waiter or waitress gets the 20% tip? So here's how you would calculate that. Let's say that you had a bill for $15.70. And you say, I want to pay that bill, of course, but I want to provide my server a 20% tip. Well, 20%, as we learned before, is the same as 0.20. 20% is 0.20. So what we can do is we can take 1570 and multiply it by 0.20 to find out the total amount of the tip. 1570 times 0.2 is $3.14. So the tip is going to be $3.14. Now, the total amount of your bill then is going to be $15.70 plus the $3.14. So you would want to leave 7 plus 1 is 8, $18.84 with a $3.14 tip. Another way to do this is if you wanted to calculate the total amount without having that intermediary step, and you still want to give your server a 20% tip, multiply it by 1.20. The 1 is the total amount of the bill to begin with, 100% of your tip. So 100% is the same as 1.0. You just move the decimal 2 places to the left, and that's 1. So 1, and then the 20% is there. So you just multiply 1570 by not $1.20, but by 1.20, and you'd get the same number, $18.84. That would just save you a step mathematically to calculate the total bill that you would want to leave for your server. And there are some other illustrations in there as well, as far as examples go. Page 268 and 269. Try the exercises in the back of the chapter, back of chapter 6. So we'll do a couple of them here. If you turn to page 274, let's look at number 63. What is 26% of 480? What is 26% of 480? So we're going to use the method where we convert the percent to a decimal. So we move the decimal 2 places to the left. So we have 0.26 times 480. Plug that into your calculator and you get an answer of 124.8. Okay, 63 through 66 are all a similar arrangement. Now, what about if you ask the question a little bit different way? Look at number 67. And I'll write that here. 67. What percent of 30 is 45? Well, 45 is bigger than 30, so we know that that's going to be over 100%. So let's look at method number 2 that they use in the book. In this case, we do a cross multiply. So we have what percent is this value. So we do a cross product here, 30 times x equals 45 times 100, which is 4,500. We want to solve for x. So this is a little algebraic problem here. We divide both sides by the 30 over here. Any number divided by itself is 1, so this cancels out. So x is 4,500 divided by 30, which gives us 150%. So 150% is 45 is 150% of 30. Okay. Lastly, the percent increase or decrease in something. So if you have, if your salary, for instance, is based on a percentage, so you have a 3% raise, what does that mean? Okay. The way that you calculate that is you take the final value minus the initial value and divide it by the initial value. So for instance, if we wanted to look at an example from the text, if you look at number 73, after 1 year on the job, Grady got a raise from $10.50 per hour to $11.34 per hour. What was the percent increase in his hourly wage? So we look at the difference here. His later number was $11.34. We find the difference from his original wage, which is $10.50, and we get a value of 84 cents. So he got 84 cents more per hour. That's the amount of his increase per hour. So we have to look at what his original amount was. So the amount of the difference divided by the original amount is 8%. 0.08. We move the decimal point 2 places to the right, and we see that that's 8%. That's an illustration of a percent increase. Percent decrease, let's look at number 75. Number 75 says, between July 1st, 2000 and July 1st, 2007, the estimated population of Pittsfield, Massachusetts declined from 134,953 to 129,798. What was the percent decrease to the nearest tenth? So this is not only asking you to calculate the percent decrease, but also asking you to round. So what we do is we find the difference from the original population. So the original population was 134,953 minus 129, 798. This difference is 5155. And we divide that by the original amount, 134,953. That's a comma for thousands, not decimal. And this gives us a decimal, 0.038, which, to convert to a percent, once again, you move the decimal 2 places to the right. So it's 0. I'm sorry. 2 places to the right. This gives us 3.8%. So the population decreased by 3.8%. There are some other examples in the text. There are additional practice problems to work on there in the homework practice section that we did not actually cover in these examples. If the solutions are not in the back of the book, please check the solutions on Blackboard. So email me here if you have any questions, and I appreciate your time. Thanks very much. Good night.